have an announcement to make. There'll be a group photo after the third talk, before lunch. So, sandwich between third talk and lunch, a group photo. Our next speaker is Professor O Taïbi, University of New York. He'll speak on progress in the computation of discrete series multiplicities for classical solutions.
Thank you. So thanks for the introduction and for the invitation to speak here. So I'm very honored to participate in this celebration in honor of Harish Chandra. I don't imagine that what I will talk about, the very concrete arithmetic application, is something that Harish Chandra would have liked, but as you'll see, at least for me, his work and his influence was very important. So this is part of a long-term project with Gaëtan Chenevier, and so the main question is a very classical problem. So if you take G classical reductive group over Z, and you fix, let's say, by infinity, well, let's say sigma, a discrete series representation of G of R, then what is the multiplicity of this sigma in what I will denote by A2 of G, which is the space of square integrable level 1 automorphic forms. For example, when G this the multiplicity of, it's often called dk, well, plus or minus, it doesn't matter, in A2 of G is classically the dimension of cusp forms, and that's something that's easy to deduce, say, from the structure of the graded ring of modular forms. And yeah, so more generally, you have the classical version of this problem is to determine the dimension, or say dimension formulas is equal cusp forms. So my SP2n is what some people denote by SPn. So. And the thing corresponding to discrete series is this inequality on the bits. Sorry? Are those weak inequalities on the K's? Yes. So this corresponds to a algebra of GLN of C, or representation of UN, if you prefer, and that's what gives you a holomorphic vector bundle on
So this refers to the holomorphic discrete series?
Yes, yeah. So Siegel modular forms. These are. So the Siegel cusp forms. And okay, so there's the usual parameterizations of these things by integers which satisfy this. And the condition that this corresponds to discrete series is precisely this inequality. Okay, so a couple of remarks about this. So why did I put classical here? Well, it gives nice infinite families of groups, but of course exceptional groups would be interesting as well. So why did I put discrete series? Essentially because almost nothing is known in other cases, well, more precisely in representation which has same infinite character as a discrete series, we can answer this question in about the same, for the same groups essentially. But apart from that, almost nothing is known, for example, for SL3, the first case where you don't have discrete series representations. There is, well, apart from Gelbart-Jacquet lifts, we know nothing about such automorphic representations. Sorry, I didn't. I didn't get your question, I'm sorry.
Like in the obvious thing that the multiplicity of the discrete series in those automorphic form, that's exactly the dimension of the cusp forms of weight. So here when you're saying this dimension of the Siegel cusp forms,
yes. Cusp form, sorry?
Does it correspond with some multiplicity?
That is equal to a multiplicity of holomorphic discrete series. Sorry? The group is symplectic, yeah. Okay, so for example, for SL3, there is no known example of something which is not a Gelbart-Jacquet lift from GL2. And the reason for putting level 1 here, so this particular level is, well, it's aesthetically pleasing. It's easier spectrally to understand this. So it's a good first case. But as we'll see later, it makes some things harder. Anyway, these conditions, so classical, level 1, and discrete series imply that G is, there aren't so many, for example, the GLNs, or well, SLN, say for n at least 3 is excluded, so G is either sp2n for some n, or I'm going to write A special orthogonal groups as a special orthogonal group, so there's more than one, for M which is either odd or divisible by 4. And to be more precise, so it's an SOM which has signature PQ at the real place with P minus Q congruent to minus 1, 0, 1 mod 8. And which is split okay, so these are the groups that we consider today. And sorry?
Classical. Why classical?
Yes.
Refers to classical group. Refers to classical group. Among classical groups.
Yes. A classical, it means essentially type A, B, C, D. Well, A is excluded because of discrete series, and discrete series plus level 1 condition, and yeah. So the theorem is that for many of the lower rank groups, so up to SP22 and SO25, there is an explicit, well actually it's slightly more complicated than this, but there is an explicit formula for the multiplicity of any discrete series representation in this A2 of G. So let's say in terms of the Harris-Chandra parameterization of discrete series.
Can I ask, you can't have a unitary group defined over C?
No. Well, so a unitary group corresponds to some quadratic extension, and there's no quadratic extension or non-trivial extension of Q that's everywhere and ramified. That's what constrains in this case. Okay, so this follows some previous works. So for history, there's so of course the case of SO3, that's almost is really modular forms, and so the next case was considered by Tsushima. So he gave a formula he announced the formula in '83, but it was only published the proof was only published in '97. So it's actually, he worked with single modular forms of genus 2. And so his method was very geometric, so essentially using a Lefschetz fixed point formula for holomorphic vector bundles and a vanishing theorem.
Sorry, I have another very stupid question. What is the relationship of this theorem to the theorem of Langland's from the 60s about integrable discrete series?
So integrable? I'm not sure what you mean.
He gave a formula for the multiplicity of any integrable discrete series representation automorphically. I think it looks very different from what you're talking about, but I don't understand why it's clearly irrelevant.
Based on the trace formula, you mean? Or? Maybe we can discuss this later, so I'm not sure how to answer. Yeah. Also, here the interest is to have an explicit formula. So explicit means that it can be evaluated, and I'm going to add by a computer because, well, for example, Tsushima's formula is half a page already, and you can. Right. So that would be the case where you put a level which is neat or, in classical terms, torsion-free.
And furthermore, the torsion is compact, like
Yes.
Lagrange's formula.
So that was mentioned, but anticipating a little bit. Actually, for geometric things, level 1 makes things more complicated. I'll come back to this. Okay, so then there was work by Chenevier and Renard for the groups SO7 and SO9, and also, so in this formulation, SO8, or let's say most discrete series representations. And that was using definite, so signature, let's say P0 or 0Q, it doesn't. Orthogonal groups. So in this case, I want to say a bit more. So automorphic forms are very explicit, so you want to isolate. Let me write sigma instead. I guess you want sigma dual. This sigma is just a finite dimensional representation of the compact group G of R, and you can identify this with a finite direct sum like this, where the L's are isomorphism classes of even, so definite, even, and so either unimodular in even dimension or two modular lattices. So in odd dimension, that's what gives the good notion of what gives you a good reductive group over Z. What is it's actually sigma. Sorry. So yeah. Let me write it like this to not mix. Okay, and so I don't know if you're familiar with lattices, probably not, so since most of you are interested in representations theory, so just to give you an idea, so in just restrict to even dimension. So in dimension 8, there's just one. That's E8. 16, there are two. It's just double E8 and also some E16. In dimension 24, there are 24. It's classified by Niemeyer. And in dimension 32, well, there are at least a billion lattices, so something is happening here. And this lower bound by King was obtained following a suggestion of Borchet's, and is an improvement on getting a lower bound using the classical mass formula. And then myself, so it was also published the same year, but it was done slightly after. I did 2n for most 7 and SOM for m less than or equal to 13. And then more recently, with Gaëtan Chenevier, we improved this to up to SP16 and SO17. And yeah, the difference between this and this is half of the method is completely different. And so of course there are many more mathematicians who have worked on similar explicit dimension formulas, but in other contexts. So yeah, the subject was particularly popular in Japan, well, or still is. Okay. So at this point, I have to. Sorry. So you can translate between inner forms. That's the.
The answer is the same for SOM?
If you know how to do it for one SOM, for a given M, you know how to do it for all the M's. Sorry, for all the inner forms, same M. Okay, so for the other signatures, essentially. And that's what I'm going to say right now. So these are Tsushima that rely on Arthur's endoscopic classification. For the discrete spectrum. For quasi-split classical groups, so in this case split, and the extension that I checked for for certain inner forms which cover all these SOMs. And so at this point I have to say a little prayer, I guess. So I have to warn you that so the classification relies on papers that have been announced but have not yet been published. Okay. This? Yes, it follows quite easily from the definition. Well. Sorry?
The strong approximation does not work in this case.
No, you're right.
Like a group which is compact at infinity.
Yes.
So there could be some double
Yeah. So that's why this thing has more than one element. So there are finitely many such isomorphism classes, but more than one. Well, it here more than one. Yeah, that's why. But you can write. Well, you can interpret this set as you imagine as a double quotient with G finite delta in the middle.
Typically the group SOL is trivial. Typically the group SOL is trivial.
Well, yeah, here no.
Sorry?
Here no. There are some heuristics for large dimension, but none of these have trivial automorphism groups here. So far from it.
32?
Sorry?
In dimension 32?
No, in dimension 32 as well. So this lower bound may be, okay, so it's a long digression, but so this lower bound may be separated according to the root system that is in each lattice, and what contributes the most are not the ones with empty root system. So, and as soon as you have a non-empty root system, you have at least the Weil group in its orthogonal group. So, yeah. Okay, so I'm not going to attempt to explain the endoscopic classification today, but let's just say that it translates between these automorphic representations and in our case level 1 or to 1, say algebraic automorphic representations for general linear groups over Q. And just very quickly, the reason for that is because of the nice shape groups. So let me remind you of these Langlands groups. Types B and or swapped. And yeah, so it's I guess a simple exercise in representation theory. Between, sorry? This? The difference, I'm considering this as a group over Q, or even Z, and these are really complex groups. Oh, right, now I know what you, okay. I thought you were saying that duality is an involution. Okay, thank you. So it's really a simple exercise in representation theory to express, if you take any gamma, the morphisms from gamma to such a G hat in terms of self-dual linear representations of gamma. And well, that's essentially why this endoscopic classification has a chance of working. But I'm not going to say much more than that. So let me be more precise about these representations of general linear group. So if you homomorphic hospital representation for, so we can work with PGLM in level 1, and that's up to twisting that simplifies the definition. So we say that pi has level 1 if for any prime p it's unramified. So you decompose it as usual as a restricted tensor product. This has invariance and hyperspecial. And we say that pi is algebraic if its infinitesimal character, so defined by the Harish-Chandra isomorphism, so it's some semi-simple conjugacy class in the Lie algebra SLM over C, has all of its eigenvalues which are half integers, say W1, Wm like this, and we want them actually to be integers up to twisting, so the difference should always be in Z, so they're either all integral or all half integral. And okay, so I should introduce the motivic weight of pi. So this I will denote by underline W, but just W of pi is 2 times the largest one. Let's call this motivic weight. And we say that such an underline W is regular if, well, so it's slightly more general than the usual. So either the WIs are distinct, or we admit one exception. So when the dimension is divisible by m, in the middle, we allow double zero.
You don't require the half-integer condition to be related to m?
To be related to... no. So when... So actually, something that is automatic is Wm plus 1 minus I is equal to Wi. So when m is odd, you always have a 0 in the middle, and so they're all m is even, they can be either half integral or integral. With this definition. And both will occur, I mean. Yeah. And right, n of underline W for the the group is PGLM, so trivial. So n of W will be the number of level 1 algebraic pies with infinitesimal character W, and perp, the number of self-dual, same thing. And okay, so that's the end of this definition. And then there's something that I want to take as a black box for today, but and there is a method to prove non-existence of level 1 algebraic pies with a given weight W. Okay, so that's a method that has matured over many years. So it goes back to the so-called explicit formula for L functions, and so it builds on work of Serre, Stark, Odlyzko, Mestre, Fermigier, Miller, and Geneviève-Lannes, and we refined it, I think, as much as possible in our 2020 paper with Gaëtan Geneviève. Sorry? So there are some W's, for many W's, but some in a, well, not quite a bounded set. That's maybe an interesting feature of this method, but sorry? It exists, yes.
So for some ways there are no level 1 forms.
So yeah, so in some cases it implies this. But okay, it does more than that. For example, if you yeah, no. Yeah, okay. So maybe just to mention Harishchandra one more time. In some cases, so essentially, when you bound the motivic weight, you can get an upper bound on this as well. So it's not just always proving that something vanishes, but it's the method. What the method does is it shows that these pies, they live in a contrived space, so you cannot have too many of them. So when you have existence, it helps you to prove non-existence, either for the same weight or for other weights as well. So that's analytic number theory, but okay, I'm not going to discuss this further today. And okay, but it leads in particular to classification results in low motivic weight. And what is maybe striking compared to the original problem, so there are many, in a sense, well, you can see it on examples, there are many discrete series representations, even in low weight, for all these groups. But what you see in this classification is that even in the corresponding motivic weights, the level 1 algebraic pies are quite rare. For example, in motivic weight less than or equal to 22, which is already much higher than Ramanujan, and so not bounding the dimension m, there are only 11 such pies. So they're quite rare. And that's maybe a motivation for computing, let's say, dimension formulas in higher rank. So I've given you some history, so you can wonder, when does this stop? I mean, you've gone up to dimension 17, why do you care about 19, 20, etc.? And the reason is, well, related to this this phenomenon here as well. So at the beginning, there are very few examples of such pies, and also Miller showed that this is empty for when you consider consecutive WIs. So WI plus 1 is WI minus 1. Or if you renormalize, if you shift them, it's just saying that the WIs are 0, 1, etc. up to m minus 1. If m is less than 27. And so the natural question is, that's quite ancient, is, so we have a rather good understanding of how the number of algebraic representations, or well, let's say representations which are at least discrete series somewhere, grows when we either vary the level or vary the weight, if we're considering discrete series representations at the real place. But there is no known heuristic for what happens if you fix level 1 and just increase m and take the smallest possible set. That's the consecutive WIs. So that's what gives you minimal motivic weight. So the question is, does there exist consecutive W such that this is non-zero? And that's equivalent to asking if cuspidal cohomology for GLMZ with constant coefficient is non-zero. And so this question actually has been answered 2 weeks ago. This. So it's a recent theorem of Caligari. Sorry, let me put it in the right order. Sir Caligari and G. And that's yes for m equals 105 and also higher m's. But okay, so that's very nice. So using automorphy lifting techniques, but you can probably guess maybe from this here that there is a chance of this. Well, it's not really in this table that it's apparent, but there is a very good chance that this is already true for much smaller m. And another interesting question then is, how does this grow as m goes to infinity? Are there more and more examples of such things? Sorry? The degree? Ah, the degree. Oh, so you know better than me. Only one. So you have, this range for the term. Yeah. Because it's cuspidal. Okay. So let me now tell you how these dimension formulas are obtained and what's the improvement. So that's a special case of Arthur's L2 trace formula, and alternatively you could use, that's the same formula but with a different proof, formula of Goreski, Kotwitz and McPherson. And well, using this particular formula is important to really to go beyond the case that was handled by Tsushima. It wasn't clear at the time, I guess, if you could really have a uniform way of handling this question. So we take G as above, and for simplicity we take it split over Z. So it's erased on the board, but if you remember the conditions on the signature that we had, so these exist for any m, of course. And we take V lambda, an irreducible representation, so algebraic representation of G of C. And then the formula is, well, some geometric expansion is equal to this Euler characteristic. And okay, so let me focus on this side first. So there's an analysis that, well, I'm not going to give details, but using so Arthur's classification. And so the representations at the real place that contribute to this are well known, since they've been classified by Vaughan and Zuckerman. And the interpretation in terms of Arthur parameters was explained by Adams and Johnson. And as Jeff Adams mentioned, sometimes you have strictly more than one definition of Arthur packets, and that's an instance. So Adams and Johnson constructed these explicit packets. And because we use Arthur's classification, it's important to know that they're the same, because these ones are very explicit, and these ones are the ones that occur in the global theory. And so these were compared. So the two notions of Arthur packets at the real place were compared by Ancibiat, Meuglin, and Renard. And so this analysis, so it's a like heavy inductive machinery, but it implies that this thing here is something non-zero times the number of self-dual level 1 algebraic automorphic representations of a certain weight, which is regular, and then that's, you have some explicit recipe in terms of lambda, plus some error terms that are induction. So this analysis, well, this part here is really important to understand these error terms. But okay, I'm not going to say much, but let's just say that it works by induction. And in this induction, maybe I can just mention, it's important to handle all the cases at once, so together, so the symplectic groups and the special orthogonal groups. And that's one of the reasons why we cannot always use definite groups. There are no definite inner forms of SP2N which are unramified at every finite place. And for example, you really have to understand the case of SP6 before doing SO8. So that's why there's a most here. Okay, so the right hand, the spectral side essentially computes these numbers here, and all regular W's, let me put it vaguely, occur as W lambda for some pair of G and lambda. So up to error terms, these are really the same things, all the n perf of regular weights and these Euler characteristics. Now for the geometric side, so it has some main part again, and what I want to call parabolic terms, which again are handled by induction. So I'm hiding many details, but okay. Just to mention Harish-Chandra again, an ingredient in parabolic terms is some explicit formulas for the Harish-Chandra characters of average discrete series in our packets on non-compact maximal tori. And this, so this most interesting part of the trace formula is, well, some global volume as a sum of certain conjugacy classes that I'm going to explain right now. So the right hand side in terms of GLN is expressed in terms of GLN, right? Yes. So this analysis is. Sorry? Well, the goal is to. Okay. So one goal is to compute this.
Trace formula for TLM?
No. No. That's too hard.
But the original goal was to produce
Discrete series representations.
G.
Yes. So the problem is a lot of. Okay. But the main term, the non-endoscopic tempered terms, that's this. Okay. And the other terms, understand them by induction. So once you have all of these, you can revert the analysis and you can give the multiplicity of any discrete series representations, or more generally any Adams-Johnson representation in the discrete automorphic spectrum. It's the same analysis, well, in both directions.
But we didn't need to mention this rising side here, right? Because you're saying that there is a complicated inductive argument in order to reduce the calculation to this T-geometry. And now you're computing this T-geometric on the geometric side of the trace order, on the stable trace order.
Yes, so what I've explained so far is computing these in all dimensions less than some number is equivalent to computing the elliptic terms for groups in rank less than a certain number. These two are equivalent. Okay, so we have a volume here that's essentially a product of Tamagawa number and special some values of Artin zeta functions at non-positive integers, I guess. So this can be expressed as using generalized Bernoulli. So this is very explicit and computable. This is this is very elementary, so also explicit. But I'm not giving details. This part here, well, if you're just looking for a conceptual formula, you can leave it as is, but if you want to actually evaluate formulas, let me just mention that this is computable. In fact, there are at least 3 different algorithms to compute this, and maybe 2 of them are good enough to be really computable in the dimensions that I mentioned. And so the main difficulty is this. And so the sum here is over conjugacy classes gamma in G of Q, such that gamma has finite order, and gamma is G of the finite orders to some element of G of Z hat. Otherwise, this orbital integral here vanishes. So the first strategy, the one that I maybe let me add. First strategy in my paper is just compute. I was young and brave, so I just computed these orbital integrals. So I gave an algorithm to compute these orbital integrals, and it worked up to the ranks that I mentioned at the beginning. Okay, but it's okay. So it's quite delicate. There's a lot of case by case in these algorithms, and okay, I didn't consider the complexity in the sense of computer science very carefully, but the amount of time that it takes to compute these in a given dimension grows very, very fast. So it seems you're at an impasse. A second strategy is so what we call an effortless method. You just rewrite this so you group by conjugacy classes under G of Q bar. You have this, you get a formula that has this shape. Well, you have to think a bit to really show that these are rational numbers, but okay, it's true. And let's call these masses. And since we know that there are interesting new contributions for many lambdas, in let's say small rank, sometimes we can just solve a quite large linear system to recover these masses. Okay, so you use it in the other directions. You know the spectral site for certain lambdas, just because there are inductive terms that you understand, and there are new terms that just happen to vanish by some other argument, and that gives you linear relations between these masses, and if you're lucky, that just determines the masses. So you just invert this linear system, well, which in practice has thousands, well, has, yeah, thousands of lines and columns, but anyway, it worked up to rank 8. We go beyond this, and I should say, yeah, so already for the case of SP16, this required the input of the first strategy as well, so some of the orbital integrals had to be computed directly, the kind of easier ones. So to go beyond, so what's new today, I guess, let me explain the nicer case of symplectic groups. So we can use the stabilization of the trace formula, or well, just the elliptic terms. That's due to Kottwitz. You can then, so we have nice simplification. So I didn't explain how that this actually follows from a general trace formula, but it does, and the function at the real place has a special property. It's and together with the fact that this particular Galois cohomology pointed set is trivial, is that the stabilization is very simple. It's a sum. So here we group gammas up to stable conjugacy, which, well, because SP2n is simply connected, is the same as conjugacy classes over Q bar. And we have, again, something explicit times, so this time we have a stable orbital integral. And same as before. And so first, let me remind you that this decomposes as a product of all primes. And there is a function which applies to orbital integrals and stable orbital integrals, which tells you that okay, so maybe, sorry, I should have explained something earlier. So the reason I'm doing this is that there are many, in general, many conjugacy classes that contribute to the same mass, right? And we're trying to get rid of this conjugation. Yeah, that's so the function at infinity is stable, and we have this property that implies that there are no the kappa orbital integrals at the real place for kappa non-trivial just vanish. So it's very simple. So it's a product of let me put O here. So G prime is either symplectic or unitary, and gamma prime to the p to the something is 1. So it's not the same reduction that Hiraku Atobe mentioned. It's a more classical one. And these typically have well, sometimes have smaller dimension than G. And because of this, so using also that some stable orbital integrals are easy to compute, you get that P2m, m less than or equal to n, is, well, knowing this is really the same as knowing the stable orbital integrals when G prime has rank less than or equal to n. And that's actually very useful. So for n equals 11, the number of such places is 20,000 something, and the number of new things that you didn't get from an inductive argument is just 266. So that gives you a great improvement for this second strategy, just because the number of unknowns has decreased considerably. Okay, so that's not quite enough actually to do all the cases that I mentioned. There are also technical improvements in the computations, in the direct computations of orbital integrals, but I don't want to talk about that today. Let me just finish quickly with a few words on the harder case of special orthogonal groups. So now all of these kinds of fall apart. So this is non-trivial. So first, if you stabilize, you're going to have something more complicated. But okay, something that is morally equivalent is you can express orbital integrals as linear combinations of certain stable orbital integrals. So that's the fundamental lemma. That's a theorem thanks to Ngo, Valspurger. So we need a semi-simple so-called GH regular case. So not always regular. So that's due to also Cod fits and Lagrange-Sherstadt. So there's another complication that in the orthogonal case So because the groups are not simply connected, stable conjugate is not the same as conjugacy in G of Q bar. So there are additional invariants that you have to take into account, and so you don't have such a simple picture like this. But there is something. But it doesn't quite as well because of this complication particularly. So we also have to use. So there's there's something here, but I can give details, fortunately. And so to conclude, we also have to use the masses for SO23, 24, and SO25 by Gaëtan Chenevier. So the problem is, so with the previous method, we stopped at SO17, and then there are no definite groups until these ones, right? So we're missing SO19, 20, 21, and we have no definite groups for which it's often easier to have these concrete algebraic automorphic forms and direct computation. But using these masses, we can derive some lower dimensional stable orbital integrals by, so there are tricks to embed them in these higher dimensional masses. And that's how we, using all the previous techniques, so this here and the direct computation of some orbital integrals that are not too hard to compute. That's how it works in the end up to SO25 and SP22. Okay. My time is up. Sorry. Thanks for listening.
Wait for 5 minutes for the next lecture. Please feel free to question him.